Let us start with the next concept, that is Charles' law. We have studied up to Boyle's law and we are discussing numericals based on Boyle's law also. Now let us start with Charles' law here. So this Charles' law is nothing but the temperature volume relationship. So you always remember Charles' law. This is temperature volume relationship. Temperature volume relationship. Okay. Means at Boyle's law, this happens at constant temperature, and Charles' law, it is at constant pressure. So always remember this. At constant pressure means Charles' law, and at constant temperature means it is related to Boyle's law. So here I'll write the same statement for this. For an increase of every degree of temperature, volume of the gas increases by, this is important, increases by 1 divided by 273.15 of its original volume, is whatever the volume of the gas, and if you increase the temperature of that gas with the rise or increase of every degree temperature, the volume of that gas, it will increase by this much amount, 1 divided by 273.15 of what? Of its original volume at 0 degrees Celsius. At 0 degrees Celsius. This is important again. Means what? If you say VT, means that is the volume of the given mass of gas at particular temperature. Suppose T temperature, you can denote this by VT. That will be equal to V0. This is V0. This is the volume of the gas at 0 degrees Celsius. So it increases by T divided by, or 1 divided by, actually this is T divided by 273.15 into V0. This you can number at equation number 1. So here the statement says that for an increase of every degree of temperature, volume of the gas increases by this much amount, 1 divided by 273.15 of its original volume at 0 degrees Celsius. So whatever is the volume, that will be V0 at original volume at 0 degrees Celsius. And this is the volume at particular temperature, means by increasing some temperature, you will get VT, means at particular temperature, that is T. Okay, so you can denote this as VT. So this is the rise. So why do we have to multiply this quantity by this V0? Because for every degree rise of the temperature, this much is the volume that it goes on increasing. And so this much amount you have to add to this original volume. So this will be your equation number 1. So what are these VT and V0 here? This is the volume at T degrees Celsius of the given mass of the gas. Whatever is the mass of the gas, the volume of that particular amount of the gas at T degrees Celsius, and V0, this is the volume of the gas at 0 degrees Celsius, isn't it? So now if you rearrange this equation number 1, we'll proceed further. If you rearrange this equation number 1. So I'll write this equation again here on this slide itself. This is your equation number 1. This is V0 plus divided by 273.15 into V0. This is your equation number 1. Now, if you rearrange this equation, you will get your Vt, that will be equal to V0. You can put common out here. So it will be 1 plus T divided by 273.15. Okay. Now again further you can write this as Vt equals to V0. Now simplify this. This will be T plus 273.15 divided by 273.15. You are taking here LCM. So this will be our equation number 2. Okay, so you can write here, this is your equation number 2 here. This is simple mathematics. Huh? So further you can write. So instead of this 0 degrees Celsius, you can write for this 0 degrees Celsius here. This will be your 0 degrees Celsius equals to 273.15 Kelvin. This is Kelvin. Okay. Now again further you can write this equation as Vt will be equal to V0 into T small t suffix divided by T0. This will be your equation number 3. Now what is this capital T? This is the temperature in Kelvin. So you can write temperature in Kelvin. You can denote it by capital T. So that will be equal to T degrees Celsius plus 273.1. Means this is capital T, you express in Kelvin, and this is in degrees Celsius. When you add these two, you'll get here Kelvin. Now T0, what is this T0? This is nothing but the 273.15, because this 0 degrees Celsius equals to 273.15. You can see here. Okay. Now what is this TT? This is the temperature in Kelvin. That will be T plus 273.15. Okay. Now, if you rearrange this further, you can get here. This is Vt divided by Tt equals to V0 upon T0. Okay, means this equation number 3, you can rearrange this way. You can write this T0 here. This T0 you can write here. So you are left with V0 divided by T0. So this is the equation you are getting here. So in general way you can write. In general way you can write here. That is V1 upon T1. I'll write something somewhere here. This is V1 upon T1. This is V1 upon T1 equals to V2 upon T2. Now, you can write again for this in common terms, V upon T will be equal to constant, which is denoted by K2. So we can write here V equals to K2 into T. If you remove this K, so you can write V is proportional to T. This is volume is directly proportional to temperature, and this is nothing but the Charles law. Means as the temperature increases, volume goes on increasing. It means that. So we have proved this thing. Now you can write the another statement for this law as at constant pressure. You always remember when you talk in terms of Charles' law, it is always at constant pressure. Pressure is kept constant. So at constant pressure, the volume of a fixed mass of gas, fixed mass of gas is directly proportional to its temperature, in Kelvin, to its temperature in Kelvin. Means that V is proportional to T. This is nothing but the Charles law. Okay. Now here is the one more concept, that is absolute zero temperature and Charles law. Here comes the concept of absolute zero. We have talked about this. That is 273.15. So what is this? This is absolute zero temperature. So here absolute zero temperature and Charles law. Charles law. Okay. Now in practice, all gases liquefy at a temperature higher than, so gases they liquefy at temperature higher than minus 273.15 degrees Celsius. That is 0 Kelvin. This is 0 Kelvin. This is 0. This is 0. 0 Kelvin. And this is nothing but what we call as absolute zero. Means what? All gases, they get liquefied at a temperature higher than this quantity, minus 273.15. That is at absolute zero, all gases, they get liquefied. And this is the lowest temperature that can be imagined, and but practically it cannot be attained. Means you can imagine that temperature, but it cannot be attained practically. What is this? This temperature, what we call as the absolute zero. So all the gases, they get liquefied at this temperature. It is minus 273.15. That is nothing but a 0 Kelvin. But this temperature cannot be attained practically. Now here you can draw one graph for this. I'll try to draw here. This graph can be drawn this way. That is temperature on x-axis in degrees Celsius and volume on y-axis. At particular pressure, because we are talking in terms of Charles law, so the pressure should be constant. Suppose at particular pressure P1, this is the graph you are getting. Means as the temperature increases in this direction, the volume will also go on increasing. You can see from this nature of the graph here. So as the temperature increases, volume also goes on increasing. And this type of graph of volume versus temperature at constant pressure, this is called as isobar. Isobar means at constant pressure. Now if you take another temperature, suppose at P2, so you are getting the same type of pattern of the graph. That is, as the temperature increases in this direction, the volume also goes on increasing. Means if you take this particular point, this is the temperature, this is the volume. If you further increase this temperature, again the volume will go on increasing. So from the nature of the graph, you can see that as the temperature increases, volume also goes on increasing. So temperature increases in this direction and volume increases in this direction. You can see here, if this is the temperature, this is the volume. Again, if you increase the temperature, volume will again go on increasing and so on. So this is about the isobars. So such type of graph, it is called as isobar. Now at constant pressure, this gases expands on heating. Gases expands on heating and contract on cooling. Gases expands on heating and on heating and they get cooled, and when they are cooled, they contract. When they are cooled, they get contract. They contract and when they are cooled. Okay. That is hot air. It means that hot air is less dense than the cold air. Means hot air, it is less dense. Means if you heat air, it will become less dense than the cold air. For example, hot air balloon or human lungs, or the when pool floats in the swimming pool. These are the some of the examples of the Charles law. Now coming back to this graph again, as we say that this gases, they liquefies at this particular temperature. Means if you extrapolate this curve further, yeah, this like this and this also, so you will get such a point. You'll get such a point that here somewhere here, that this is the temperature, that is minus 273.15 degrees Celsius or 0 Kelvin. This is not okay, this is 0 Kelvin. So at this particular temperature, all the gases, they get liquefied. Okay, and this is nothing but it is called as the absolute zero. What is it? This is the absolute zero. This is the absolute zero. Okay. So as I told earlier also, this is the lowest temperature that can be imagined, but this it cannot be practically attained. So this is all about the Charles law. So when you talk about the Charles law, that is where volume is directly proportional to temperature. V is proportional to T. This is important. When V is proportional to T means at constant pressure. Okay. So in the next video, we'll talk about the Guy-Luzzat's law. Thank you.